So that's just a few of the ways that we can get variability with just carbon and hydrogen. And molecules that have just carbon and hydrogen, we call them hydrocarbons. Um, we have hydrocarbons in our body, mainly stored up in fats and lipids. And because hydrocarbons, carbon and hydrogen, share electrons very well and very evenly with each other, which is to say they are just nonpolar covalent bonds. They are not polar. And as such, they don't react with water very well. And our bodies take advantage of this and use that hydrophobic nature of hydrocarbons in ways that we'll see later on. But fats that are our main organic form of hydrocarbons in the living sense are a good way to store chemical energy. And it's usually a way that we deep store chemical energy. So if you absolutely need some energy because you haven't eaten in a while, you'll start to burn fat. But it's hard to get to that point where you start that process of burning fat, which is one of the reasons why people are just maniacal about doing exercise to try and burn that fat. It's very hard to get rid of because it's there for it's there to be stored for long term. So if we were to look in a human adipose cell, what we'd see is that there are a number of fat droplets, or these kind of little, here they look like circles, but in 3 dimensions they're little spheres full of fats that are in that shape because they're trying to get away from the water. They don't mix with the water. Oil and water don't mix. Fat and water don't mix. But a fat molecule, which we'll talk about a little bit later on towards the end of this chapter, are made up of hydrocarbon chains. And here you can see we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. A lot of carbon atoms completely surrounded by hydrogens, and then this bit that's going on here, which is not strictly hydrocarbon, but I'll tell you what that is later on. I'm not going to reveal all my surprises right now. Here is a hydrocarbon that you may have heard of. This molecule here is octane. And where have you heard that before? I don't know if you're talking to your computer or not, but octane is in gasoline. And octane is a hydrocarbon with 8 carbon atoms, and the rest of the bonds are filled up with hydrogen atoms. And that's kind of what this ball and stick model shows you here. And it's octane burns very well. We can break those carbon-hydrogen bonds, break those carbon-carbon bonds, and in the presence of oxygen, and release a lot of energy, which is enough to drive your engine. This down here is a way that organic chemists, it's a shorthand that they use to draw something like octane. So we've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8 points in this squiggly line. And whenever we see a point, we assume that there's a carbon atom there, or at the end of the carbon, at the end of the line. And then you just assume that if there's not anything else there, it's going to be a carbon's going to have a hydrogen attached to it, because that's the usual case. So you may see some of these squiggly lines drawn in molecular representation for the rest of the semester, and you should just hopefully understand that that's what's going on. Is it's that organic chemist and just generally a chemist shorthand, so they don't have to draw in lots and lots of carbons and hydrogens, because some of these molecules get really big, and it'll take you a long time to draw in all of those individual carbon and hydrogen atoms. Okay, so another way that I kind of alluded to before that we can rearrange carbon is through these things called isomers. Isomers might sound a little bit like isotopes that we talked about before, but they are different. Iso, again, means the same. Something is the same. Mers, that prefix mers means parts. So isomers have the same parts, but they might have different structures and different properties. And I already sort of alluded to that with the straight chain of butane and then uh, isopropane. So those are two different structural isomers that had the same molecular formula. Those were both C4H10, but they have different arrangements of the covalent bonds. So those are structural isomers. I will tell you about cis-trans isomers and enantiomers in the next couple of slides. So here's a picture showing, here's butane, 1, 2, 3, 4, and you can go ahead and count these hydrogens, there are 10. Then if we take this carbon and its 3 hydrogens off here and swap it out with one of these hydrogens, we get this molecule, and it's not going to be exactly the same in its chemistry. It's going to have a different properties like a boiling point and freezing point and things like that. Just because we can rearrange the carbon atoms, the covalent bonds, in a number of different ways. Okay, geometric isomers or cis-trans isomers are different across a double bond. So you can see here on the left, we've got this red atom here. We've got another red atom down here, but it's across the double bond. So here's the double bond here, just like we saw in ethene or ethylene. So this molecule is different from this one over here, where you've got the two red atoms that are on the same side of the double bond. So remember, this double bond prevents that bond from spinning. So this is a very planar molecule. So cis means on the same side. Trans means across. So if you think about like transportation is getting across something, getting from one point to another. So cis is on the same side. Trans is across. Okay, and we'll see practical examples of all of these later on. And then enantiomers are difficult to explain in 2 dimensions. If we had 3-dimensional molecules in front of you, it would be a lot easier to see. And what you can see is happening here is that you've got 2 different carbon atoms, and each of those carbon atoms has 4 different atoms, types of atoms attached to it. A white one, a red one, a green one, and a blue one. Okay? All 4 of those atoms, or we call them substitutions, all 4 of those substitutions are different. And when that happens, carbon has this strange thing that happens where you get mirror images of atoms that don't have exactly the same properties. Or another way of saying that is you have left-handed and right-handed molecules. So if you ever played baseball or softball and you had to get a glove, you know right away if you have the right kind of glove, if it's a left-handed glove or a right-handed glove. A right-handed person can't use a left-handed glove, and a left-handed person can't use a right-handed glove, because those 2 gloves are fundamentally, they're made of the same material, but there is something that's fundamentally different about left and right-handed gloves. Okay, so here's just another representation of structural isomers, and you can see it's just a different arrangement of the covalent bonds with the same complement of atoms. With cis and trans isomers, you can see here the 2 X's are on the same side. Cis is on the same side. So just remember, cis is on the same side. So the substitution is on the same side of the double bond, versus trans is across. They're on opposite sides. So you're like transporting or translating something from one side to the other. And then enantiomers, as you can see here in this bottom picture, are kind of like a left-handed and a right-handed version of a molecule. So both of these are C5H12 in this example. Both of these are C2H2X2. Not really, there's no element that's X, but it's just an example for example. And then enantiomers are like left and right-handed versions. And the way that you get those is if a carbon atom has 4 different atoms or molecules attached to it. So that left-handed, right-handed thing, very important in biological systems. So as you get molecules that have a lot of carbon atoms in them, you increase the likelihood that at least one of those carbons, if not several of them, are going to have 4 different molecules or atoms attached to them. And that can be very important, just as an example, with different drugs that we take to treat different medical conditions. So ibuprofen is used to treat pain and inflammation. It's an NSAID, non-steroidal anti-inflammatory drug like aspirin or Tylenol. But it has at least one carbon in it that has 4 different substitutions. So we've got 2 different forms, a left-handed form and a right-handed form of ibuprofen. And if you take the wrong-handed version of ibuprofen, it's not going to have the same effect. It's not going to treat that pain and inflammation. Does it do something different or anything at all? I don't know. There are examples of medications where the wrong-handed version has had bad effects, undesirable effects, birth defects caused in pregnant women who took the wrong-handed version of a medication. Albuterol is something that asthmatic people inhale. It's an inhalant that helps open the trachea, open the vessels of the lungs, and breathe better. Well, albuterol is also a right and left-handed molecule. And it turns out in this case, the right-handed version is effective and the left-handed version is ineffective. So besides demonstrating that, it's important that we know about left and right-handed versions of molecules, it's also not a universal thing where it's always going to be the right-handed version or it's always going to be the left-handed version. So R is for recto, which means right, and S is for sinistro, which means left. The word sinister comes from referring to people who are left-handed as being like sneaky and underhanded, all the same word root, because historically people haven't trusted left-handed people. And as a left-handed person, I hope you feel like you can trust me, because we are 10% of the population. Okay, so for now, from up to now, we've been talking about 3, 2, 1. Up to now, we've been talking mainly just about carbon and hydrogen and how we can change a carbon skeleton, maybe rearrange double bonds and things like that. But if we were just made up of carbon and hydrogen, it would be very hard to have any interaction with water. So, in addition to having sort of those Legos, those carbon and hydrogen atoms, we have a couple of what we call functional groups, which are commonly repeated sets of atoms that are not just carbon and hydrogen that we can attach to the skeleton to change the chemistry.